Good afternoon, everybody. Today what we're going to do is talk about a new concept for us in this class known as electric potential. And the best way to talk about electric potential, just like a lot of things with electricity, is to look at it with um, gravity first, because it's a concept that we can apply to gravity. We don't typically apply it to gravity, but we could. This picture right here shows a tennis ball being held 5 meters above the ground. We can let it go. It's going to fall down to the ground because the earth is going to pull it down. And if we were to figure out or want to know how fast it's going at the bottom, instead of doing kinematics, solving for time and all that, we can go with a real simple energy equation. So basically what we need to do is figure out the amount of kinetic energy it has, because once we have kinetic energy, 1/2 mv squared allows us to figure out the speed. Now, if I were to do this lab somewhere in our school and then go somewhere else at a higher elevation and do the same thing where I drop it from a height down 5 meters, I don't think it's a surprise to anyone that if we were to do a lab like this at in different stories of a building, we're going to get the same speed after it falls 5 meters. The earth pulls equally at all locations on the earth, which means that a ball should be pulled down with the same speed. So in looking at this, it doesn't matter if I'm going from 5 down to 0, from 15 down to 10, or from 1,000,005 meters down to 1,000,000 meters. As long as that gravitational field, 9.81, stays the same, it's going to fall the same speed. If I look at our equation here, the energy that I had at the beginning is going to be equal to the total energy I have at the end, which is going to be a combination of kinetic and potential. How much potential you have depends on your height. Your height depends on where you, the problem doer, assign 0 to be. Now, if this thing lands at the ground, we call the ground 0. Simple. If I go from one tall height to another tall height, you have the option of saying it goes from 15 down to 10. You could also say this is my 0 line, which makes this my 5 line. So I'm looking at my options here as I scroll down. I subtract away, I take the difference. Taking the difference is delta. And so what I have here is the change in my potential energy equals my kinetic. So it's not potential equals kinetic, it's technically, and it's always been, change in potential is equal to our kinetic. If I look at the right-hand side, equation for potential minus equation for potential, m and g remain constant. So what I can do is I can simply look at it as mg times the change in height. So again, all that matters is the change, not the actual individual values, because those individual values depend on where we decide 0 to be. So if I look at my final lines here, it's the change in potential. And what I should probably do is put that in italics. Change in potential is what matters, not the actual energy, because the actual energy depends on your choice for height 0. As I've told you from the start, you get to decide where 0 is. Pick something convenient. Now, what's the whole point of all this? The whole point of all this is that change matters, not actual value, but change. Now, for us with gravity, we are always looking at one single object moving from one place to another. When we start looking at charges, it is not uncommon for us to have a very, very large amount of charge. We're talking, millions or billions of charges all moving along or all building up. So with that in mind, we might have a whole bunch of charge moving through, and so looking at just one single doesn't make a lot of sense. So this is where we look at our new concept known as potential. This would be G for gravity. U is potential energy. This is gravitational potential energy. This, G, gravitational, this capital V stands for potential. They sound really similar. Potential energy, potential. Obviously, the word energy is missing here. What this is a ratio of energy per particle. So for every kilogram of mass I have, This will be the amount of energy that I have, and that ratio gives me my potential. M times G times H, I notice that the M cancels out. So my gravitational potential doesn't depend on the mass. It can be found using the mass, but it doesn't depend on the mass. It depends on the gravitational field and my location. Now, oftentimes in physics we get a little bit lazy, and if we were doing this together in class it wouldn't be a big deal, but now that I'm not here directly in front of you, it might be smarter. We should always have a delta here because again it's the change that matters. So what we could do is we could throw in a little delta symbol here, something like that, because potential is technically always talking about a change. Over here, we would just have to put in a delta in front of that H there. So let's see if I can do that real quick, and let's see if I can do it actually small enough without just ruining everything. So that's really what we're looking at. We're always looking at a change. How does the potential here compare to there? Because that's what matters when it comes to energy. So if I look down here, this right here, this might represent the stairs that we have in our school. If I step up one stair, I just increased my energy, 1 unit of energy per kilogram that I have, perhaps. If I take a second step, what happens if I walk back and forth across that step? Do I get any higher? Do I change my potential? I don't think so. So everywhere along this dotted line is going to be the same amount of potential, the same amount of potential energy as well. And because on Earth we have a nice uniform field, every step up gives me the same exact change from 1 to 2 to 3. I did some copying and pasting and that sort of thing, so I know that this line here is exactly twice the size of that line, so I get up to 6. So these lines show me which height I am at and therefore what my potential is. If I scroll down, we would call these contour lines. In map class, in my wilderness survival class, we would call these contour lines, showing us the contour of the ground that we stand on, the height. But in physics we call them equipotential lines, and hopefully equipotential lines, hopefully that makes sense. Equa, equal, potential, potential lines. So these are lines showing us where our potential is the same everywhere. So if we scroll down a little bit, what happens if I zoom out from the Earth? Well, if I zoom out from the Earth, those equipotential lines, locations where I have the same potential, start to turn into circles, right? If I stand over here in the United States and I move up a particular height, I get here. If I'm over in Australia and I stand up on the same exact height, I get the same amount of potential. And so same everywhere around the globe, which means I end up with these equipotential lines that are circles. And I go a little further away for 2, a little further away for 3. This right here could be a picture that represents a tropical island somewhere in the ocean. This right here would represent sea level. This right here is showing me some kind of a sea mountain with the X representing the summit of that mountain. That's typically how you would see that on a contour map. And so what I find is that all these dotted lines are showing me locations of the same height. When you're using this for navigation and for travel and for fun maybe because you like maps, you're not thinking about physics. But we know that in physics we can take this height and we can relate it to energy and to potential. So these lines aren't just showing me what my height is, they're also giving me an idea of what my potential energy is, what my potential is. So I've got these different lines. What happens if I hiked from red dot number 1? What if I hiked exactly along this dotted line? Now these dotted lines aren't actually traced on the ground. Hopefully that's an obvious one. But if I were to hike this way, what I'm doing is I am staying at the same exact elevation all the way around. Even if it's really, really steep here and like a cliff, or if it's more gradual over here, I am staying at the same height. I'm not going up, I'm not going down. And what I notice is what happens if I get all the way over here to point 2? Point 2, same exact height. So if I go from 1 to 2, I'm going to have the same I'm going to have the same height at my beginning and ending location. I'm going to have a change of height that's going to be 0. I'm going to have a change of energy that's going to be 0. I'm going to have a change of potential that's going to be 0. And it doesn't matter how I get there. I can follow this line and never change my height at all, or I can walk straight to the east, go up over the summit of the mountain, back down, and what's my total change? Well, I just gained 3, but then I lost 3. My total change is still going to be 0. In physics, we call this path independent. It does not matter how you get from point 1 to point 2. Once I get from point 1 to point 2, I'm going to have a particular change. It doesn't matter how I do it. I might gain a little extra along the way, but I'm going to lose that along the way as well. So again, these are contour lines, and contour lines in physics can be shown or can be used to figure out what your potential energy is, or your energy ratio, your potential is. So this right here is a slide that's included for you, and we would have done this together in class. And again, what we have is our gravity column. So I'm going to look at gravity first, and then switch over to our electric potential here in just a second. So field, gravitational field is G, newtons per kilogram, which actually converts into meters per second squared, which is why we can use free fall acceleration as G. But this right here is our gravitational field. For every kilogram you have, you're pulled down with 9.81 newtons. The equation to find the force. All right, well, I have force equals mass times G, which is actually the equation for field rearranged. G is equal to the force divided by the mass, newtons per kilogram. Now it says force can be too specific sometimes, so we can put it into a ratio, and there, as I just said, force to mass ratio. Continuing down, we have our equation for energy. We did that, back in January. We did our energy unit. Moving down, here's our new item, our potential difference. Potential difference V. This is an energy to mass ratio. So instead of a force to mass ratio, now it's energy to mass. So I have force and energy, which are specific to this one mass right here. I have field and potential, which are the ratios. I can find them. I can find the field by using the mass, but G doesn't depend on what the mass is. Neither does V. If I move down a little bit more, what is our unit going to be? A joule per kilogram. How much energy do I have in joules per kilogram? So it's kind of like it's kind of like a gravitational field. How many newtons per kilogram? And then at the very end, if we put our energy equation in and divide out the mass, we already did this on the previous slide. G times H, field times how far. And again, we should, because it's a difference here, we really should have put in some delta symbols there. And we'll be good about that when we go forth. So now let's apply this to actually what we're talking about, and that's going to be electricity, because it's not very common for us to have one single charge being moved around. We're going to have thousands, millions, billions of charges moving perhaps. For force or for gravity, you got one thing being pulled. The earth pulls on my tennis ball. The earth pulls on you. The earth pulls on the car. Here we're going to have a lot of particles, which is why it's going to be so important. Electric field, newtons per coulomb. We just got done talking about that the last couple weeks. Equation to find our force is the charge times that field, just like our mass times our field. Moving down, we have our equation to find the electric field, which is a ratio, force to charge ratio, newtons per coulomb, which means we can now find our amount of energy for a particle. That's going to be new for us. I can do this one of two ways. I can do force times distance. because work equals energy and work is force times distance. Q times E is my force, D is distance. Or I can look at it and just copy it. Mass is my particle, Q is my particle, G is my field, E is my field, H is the change relative to my field. My field always points down, so this is up or down. Well, our electric field can point any direction, so D has to be in the direction of our electric field. Real quick, go back 2 slides, boom, and a boom. What happens if I walk sideways on the stairs of my lab? If I walk sideways, I don't change my potential because gravity is pulling up and down, and I'm moving side to side. I have to move with the field or against the field to actually change my amount of potential, energy, and my height. Same idea here. Now we can't just say H because H is very specific. H means vertical. We don't always have a vertical electric field. We always have a vertical gravitational field thanks to the Earth. We don't always have vertical, so this can be any direction, which is why we use the letter D, which is much more generic than the letter H. And now we get to our potential. Notice I don't put an E right here. And the reason for that is once we get off this slide, we never use VG. VG is something that doesn't really have a lot of usefulness because, as we said, when we talk about gravity, we're usually talking about one single object being pulled. And so energy is useful. Now, we're going to use this all the time for electricity. So since this is really used for electricity only in real life, we don't bother writing down an E every single time. So big old capital V, which is why I got the little bars there. You don't have to do the little bars. That's just so that you can see in my handwriting that it's capital, because we have lowercase v already used up for velocity. So our electric potential difference right here, electric potential difference. Notice the word energy is nowhere to be found. The word energy is nowhere to be found. It's a ratio, energy per charge. So we get a joule per coulomb now, not a joule per kilogram. Now we get a joule per coulomb. And even though a joule per coulomb is a unit that makes perfect sense for every coulomb I have, this is how many joules I'm going to have, we abbreviate it as the volt. Now we had work measured in joules, we had power measured in watts, the letter W was all over the place. Here we have a volt measured by a volt. I'm sorry, we have potential measured by a volt. V measures V, so that's actually really nice. And now what we can do is we can put in our energy equation. QED divided by Q gives us just ED. So our potential, and again I should put in a little delta symbol right here, our change in potential is equal to what our field is multiplied by our change in position in that field. Do I go with or against the field? If I go with the field, it's one. If I go against the field, it's something else, positives versus negatives. So this is electric potential difference. A lot of times we just call it the potential, or the potential difference, or the electric potential. Basically any combination you want. Just make sure you don't say the word energy, because that would be incorrect. So that's what we're going to look at. It has the same application as what we did here. The contour maps and change is what matters, not actual values. That's what we're looking at here. And every time you look at V, you're actually looking at a little delta symbol right here. It's pretty common for us in physics to sometimes just kind of leave it off. You're always looking at the change, comparing one place to another. So moving forward, these are some activities that we would have done on the board, bringing you guys up here. But basically, we've got this idea here. Remember, all of our electric rules are based on what would a positive do. So if I have a negative source and a positive source, for a positive charge, every particle in the known universe will always move to a location of low energy. It's why my tennis ball always falls to the floor instead of moving up to the ceiling. It falls to where it has lower potential energy. Yes, that energy might turn into kinetic, but it always naturally moves with a field to low energy. Where would a positive go? A positive would go to a negative. which means a negative source is low energy for a positive charge. Opposite charge is a negative, obviously. It would naturally go to a positive. So for a positive, its low energy location is at the positive source. So you notice we have two opposite locations for low energy. It depends on your charge. High energy would obviously be positive. Take two positives, force them next to each other. Take two negatives, force them next to each other. If I let them go, one of those particles is going to go shooting off. Now, because our rules are based on what a positive would do, potential, since potential doesn't depend on the actual particle itself, it doesn't matter if I have positive or negative. I could have no particle at all, because here's my equation. I can say, what, this location here, what's the potential? This location here, what's the potential? And what's the difference? I don't need a charge. So we need a rule to be made. And since we have the positive as our rule maker, I roll down. Low potential is where you have low energy for our defining charge. So low potential is where you have low energy for a positive. So our negative source is always considered the low. Our negative source is going to be considered 0. So if you listen to me say, we should always have a delta symbol on here, and you say, well, why don't you? Because a lot of times we're comparing to the negative plate, and we call the negative plate 0. It's no different than you deciding where to call 0 height. You usually call the ground 0, but you don't have to. You can call it anything you want. Same thing with potential, because we're actually looking at a difference. So what we're looking at is what is the change. And if we use 0 as one of our locations, then the change is really, really easy. So what would a positive do? That is our rule maker. So 0 will be at the negative source. 0 is also at an infinite distance away, but that's going to be our next level of physics. Excuse me. That's going to be our next level of physics, which would be obviously AP physics. So that's something that we will not worry about. Right, so calculating a change in energy, we've got our energy equation here. Change in potential, all I need is my field and my distance moved. So if I read here, I need to know what is the charge magnitude, how much charge do I have, and I also need to know what the sign is, because if I move in one direction for a positive, that might be a gain, which means for a negative, that would be a loss. If I come down here, this shows me that to find my potential, I don't need to know what the charge is or the sign. All I need is the two locations and how strong my field is. So I can get a lot more information. I can get potential with a lot less information. All right, so our equations are electric energy, electric potential difference, and this right here is potential is equal to our energy ratio. If we just multiply Q over, this is how I typically write it. So basically, I have a very, very, very easy way to get from potential to potential energy. All I need to know is the charge that I have. I don't need a charge to know what potential is, but once I have a charge, I can quickly go back and forth between the two of them. And of course, I've got kinetic energy over here because I'm going to use electric energy and kinetic energy together. I can shoot particles. We can shoot charged particles. I know what the potential energy is here or here, depending on what information I'm given, and I can find a kinetic energy. So I've got my electrons and proton charge, and I've got my masses. I gave you the masses before because I told you we'll need them eventually. Well, now mass right there. So eventually has happened. So now we're going to need to know those masses. So this is one of the worksheets that is posted. So there's a picture of our map looking at the changes and the differences as we go through. Right? So some of the things that I've highlighted here for you, right, is looking at our lines here. We have equipotential lines for electricity, just like we have for gravity. only it's not going to be making a map of an island or something like that. It's going to be a map of where my charges are built up. So I can see I got lines right around here really close to a positive. I got lines pretty close to a negative. Negative is by definition my low. Call it 0. Conveniently, every one of these lines is a 1, a 2, a 3, a 4, 5, 6, and then 7. So we're told we have 7 volts of difference between the two plates. These lines show 1 volt each, 1 joule per coulomb each. If I wanted to draw the equipotential line, the electric field lines, the blue arrows, shows me what a positive would do. A positive would be pulled into this plate. A positive would be pulled into this plate. A positive would leave that plate. So the arrows still show me what a positive would do. The red lines represent equipotential. Notice there are no arrows on there. It shows me this line right here is where I have 4, 4, 4, 4, 4, 4, 4, 4. No different than me walking back and forth on a stair and getting no change in my energy. If I scroll up, rank A, B, C, D, E, and F in order of increasing electric potential. I routinely call potential, I call it a label. This spot on the floor is 5 volts. That spot over there is 8 volts. I can tell you the difference when I go from 5 to 8. I can tell you the difference when I go from 8 down to 5. One's a positive, one's a negative. So voltage is a label. And then we look at the difference between those locations to get our potential difference. So calculate the difference between our locations, our labels. What do we have down here? Right? In general, can we say that if a charged object is free to move in an electric field, it will move from an area of high potential to low potential? Well, high potential is the positive side. Low potential is the negative. Will every single charged particle always go from the spot that is, here it is, it's labeled as high potential because it's got pluses. This one is labeled as low potential because it got negatives. Do all charged particles naturally go from the positive to the negative? So that's what that question's asking. The solutions are also going to be posted on an answer key file, so you can give it a try and you can see the solutions. All right, electric field lines have arrows. It shows what a positive would do. Equipotential lines do not have arrows. If I were drawing them with you, I would actually draw them with dotted lines so that they look very different. Solid lines with arrowheads, dotted lines without arrowheads. This is showing my electric field. This is showing where my potential is the same. So for some pictures, so relating gravity back to this, right? If this is the Earth, we've got the gravity pulling straight down. We are so small compared to the Earth. So whether you consider the Earth to be big or not, based on universal things compared to the universe, the Earth is pretty small, but compared to us, it's really big. So because it's so big compared to us, we get this big source. It appears to be flat to us, and I get these blue arrows pulling straight down. These should be my G arrows. These are red dotted lines, equipotential. This is stair step number 1, stair step number 2. If I zoom away from the Earth a little bit, I start to see that curve. Okay, fine. Just take a step up. Here, makes me do this. Against that blue arrow, against the blue arrow, against the blue arrow. And I get the same height at all these red dotted locations. Notice the orientation between them. Perpendicular, always. Here I've got red curves, but if I look at one single spot, perpendicular, perpendicular. I always get lines that are perpendicular. If I zoomed all the way away from Earth, I'm going to get something that looks like this. Now, we don't want to talk about gravity. We want to look at electricity. Okay, so what I'm going to do is I'm going to throw in a plus sign. What would a positive do? It'd be shot away. So my blue arrows show me a positive being repelled away. What do the red lines show? Not very well, I guess, but it looks like I tried. This shows me the same distance away all the way around. This is where I have the same potential. What if I don't have a particle? Okay, fine. I still have a spot labeled on the floor. So I have something similar here. Here, very large source, a big plate. So just like the Earth is large to us, the big plate of charge is going to be considered a large source. My electric field points to the left because positives will be pulled in towards this negative plate, which means that I get the stair steps. If I go this far away from the plate, I'm the same distance away from the plate everywhere, same potential. Here, same potential, perpendicular. So our lines are always going to be perpendicular to each other, which I do believe I had right there, perpendicular. They're always going to be perpendicular, even if there are curves. So if I go back a few slides, that's what I tried to draw here. I did my best. Perpendicular there, yeah, I think so, yeah, I think so. Over here, my blue line's bent out a little bit as I tried to make everything perpendicular all the way through. Some lines are better than others. Right, so a battery. You got your double A's, your triple A's, your C's, your D's. All of the batteries that you typically use, the standard, Duracell, Energizer, Rayovac, AA, AAA, C's, and D's, they all have the same voltage. They're labeled, and if you look carefully, even if it's not labeled directly on the battery itself, it will be labeled somewhere on the packaging. They are all 1.5 volts. Now, what does that mean? It means that the difference between the negative end of the battery and the positive end of the battery is 1.5 volts. Now, for reasons that are chemistry related and things we'll talk about in AP physics, you've got chemicals inside your battery that force all the positives onto this end and leave the negatives here. Remember, what would a positive do? We look at positive charge motion, so we're gonna look at positives. So all the positives are built up here, all the negatives are built up here. There's chemicals inside making that happen. Because what should happen? They should all mix equally. I got all this metal inside, they should all be spread out equally. The chemicals don't allow for that. So I get a buildup of positives and a buildup of negatives. That means I've got high potential here, I've got low potential here. What's the difference? 1.5 volts. Now, no one likes dealing with 1.5 when it comes to mass, so I'm going to look at a car battery, a 12-volt car battery. That means that the chemicals inside, the lead and the acid and everything else, the way they combine together, you have one side of your battery that is at a 12 volt, it is 12 volts higher than the other side. So we just say, why don't we call the negative end 0, and we call the positive end the 12 volts. So that's exactly what we do. So this right here is a 12-volt battery, which means that anything that touches this side of my battery is going to have the same voltage, because when metal touches metal, it makes one big piece of metal. So that means this right here, this big plate, is touching the high side. So this is also a 12-volt side. Over here, negative, touching negative. This is my 0, my low volt side, which means between my two plates here, I have a difference of 12 volts. So anything that touches this, anything that touches this, is going to have the same voltage. And we still have static electricity. We still have charges stuck where they are. They shift a little bit, but they're not flowing. As soon as I add one new piece of metal, well, I now have, adding in a piece of metal, I now have a full connection. And now charges just flow nonstop from the high to the low, and I get what is called a circuit. We're not quite there yet. So what do I have in between my plates? Electric field lines. What if I drop the positive somewhere in here? It's going to go shooting off to the right. What if I drop the negative? It goes shooting back to the left. The potential is labeled as 12 volts here, 0 volts here, and if I went through, I'll have a 1 volt, 2 volts, 3, 4, 5, 6 volt line. I have a line for every single label I want. Do I want to label all 12 volts? No, I don't want to draw 12 lines. That seems excessive. Maybe just a 6 in the middle. Maybe I do a 3 and a 9 here. I don't know. It all depends. How many lines do you want? How many do you need? You don't want to go too crazy, though. Over here on the right-hand side, you have to remember, work, energy, same thing. So you might be asked, how much work is done on the particle? What is the change of energy of the particle? How much potential does it have? You got to remember, they're all related. Work can be force times distance, or I can look at work giving me a change in energy. So if I roll down a little bit here, energy is equal to QV. So once I have one of these values, just get you Q, and the other value is very easy to find. All right. So these are samples that you can look at. They are on the slides that are posted for you, the PDF. So I've drawn my own equipotential lines. There are no arrows. So I've got 2 volts, 4 volts, etc. Is it possible to have negative voltage? Yes. If you decide that one location is 0 and you have something lower than that, then yes, you can have spots that are labeled as negative, just like I can have negative heights. If I call the second floor height 0, when I go down to the first floor, I must have negative height. So yes, you can have negatives. We try not to because it doesn't make a lot of sense. So I'm going to go with 2, 4, 6, 8, 10, 12. I've got a couple locations here. What is the change when I go from A to B? Looks like I'm increasing. From C down to B looks like a decrease. Drop in 2 coulombs of charge and start going from A to B. Well, once I know what my delta V is, finding the energy is really easy. All I have to do is add in my charge. So you can give that one a try. The solutions are down there for you with some explanations, so you can check those out either on this video by scrolling through slowly or by looking at the notes that I've presented to you. Here, positive particles move to the right. Well, the field points to the right. So if I positive moves to the right, we're going to lower energy. When we go with the field, when a particle naturally does what it does, it goes to lower energy. So we're going to have a loss in energy if we go to the right. If we go to the left, it'll be a gain in energy. The solutions are there posted for you. All right, so for now, I think that'll be a good place to stop looking at electric potential. There are some worksheets as well as some answer keys that are posted for you to look at. These notes are also posted, so you can look at those. That should be lesson, where are we at now? We're on week 6, I suppose. So time is flying. So you'll find those on the appropriate lesson. And what we'll be getting to very, very soon is going to be voltmeters and capacitors. Voltmeters are actually very, very easy things because we know what voltage is now. It is a difference. It is a difference between any 2 locations. So what does a voltmeter tell you? It's this little electrical box that shows you. And you know what? Let's do a quick search so you can actually see what they look like. Voltmeter images, there we go. So you got them all. So this right here, standard voltmeter. So what you have here, you've got a red and a black. We call them leads, we call them probes. Basically, you've got a red and a black coded wire. You got a digital readout here, and what do? You turn it to the proper setting. I can measure high and low voltages, so how fine-tuned do I want it to be? And I just touch the 2 locations. Literally, these are just metal spikes. I literally touch 2 locations, and it tells me what the difference is. I can get positives or I can get negatives because it's a difference. So A minus B versus B minus A, they're opposites of each other. So it gives me a positive, it gives me a negative, and it gives me an actual number. And a lot of these can give me other things as well. So a lot of times you'll see it called a multimeter because it can measure multiple things, not just voltages. But we typically call it a voltmeter, which is why all these things pop up when I type in voltmeter. It's why all these different things pop up. And these things are pretty reasonable. You can buy yourself some pretty cheap ones that do the job. So if you ever wanted to kind of play around and tinker, you go to Ace Hardware, you go find the voltmeter section, and they'll have something there for under 20 bucks if that's something that interests you. Here you got old school physics voltmeters that we never use. We always use the electrical ones. So in looking at our voltmeter, it's always wherever the red meter is minus whatever the black is. So the black is usually called the ground. So I subtract, what's the difference from black to red. So as we go from black to red, so we take our red value, final, minus the black value, initial. So the phrase that we use with a voltmeter is you always lead with red. Red is the location that you are interested in, and where did you come from is the black. So if we were to do this in class, I would have my red and black pen so you can see the different colors. So if I have a positive plate here and a negative plate here, I know this is my high potential. I know this is my low potential. If I placed red and black here, the red location high minus the low negative location gives me a positive reading. If I roll down just a little bit there, if I had something like this, if I see these blue arrows pointing this way, that means this must be my low, this must be my high. Well, if I look at this, my red is on low, my black is on the high. If I take my low value and I subtract away my high value, I get a negative. So all it takes is me taking these two wires and switching them back and forth. If I go red and then black, if I switch around and go black and then red, all I'll get is a switching of the sign on my voltmeter. So again, this is our electric potential, oftentimes referred to as our voltage, and it is a difference between two locations. That's what it always is. Anytime you see it without a delta, just realize we can compare it to 0, which is usually our negative plate. Right? And then what we'll do is we will eventually get into looking at capacitors, and we'll do that here in the next few days. We'll start looking at capacitors. So these are the slides right here that'll come with that. Okay, so those are our notes for electric potential. There's some worksheets you can look at, try them out, check the solutions. We'll eventually have an online assignment that will go with this as well. So take a look at that, and if you have any questions or anything, make sure you bring those to our Zoom meeting. So until then, we'll see you soon.